Hello, everyone, and welcome back. In the previous 20 or so lectures, we've seen how we can use definite integrals to answer real questions. Some of those questions were geometric in nature, so asking for the volume or the area or the surface area of objects, whereas more recently we've seen how to answer more physical problems, such as computing the work to move an object over a distance. Now, one thing that all of these problems have had in common is that the integrands, the thing we're taking the integral of, has been relatively basic. That is, it's really just been sums of multiples of functions of the form x to the power of n. And in this case, finding the antiderivative is relatively easy, right? We add 1 to the exponent and we divide by the new exponent. We've combined this with the substitution rule, and we can get slightly more complicated integrands. But the question is, how do we move beyond these relatively simple functions and start addressing more complex functions? And that's exactly what we're going to do moving forward. We're going to start talking about what are called transcendental functions for the next few lectures. And in particular, in today's lecture, we're going to focus on the natural logarithm. Now, we've probably seen the natural logarithm before, and we always, or at least probably have always seen it come up in the context of the exponential function e to the power of x. And we've seen how it can be viewed as the inverse of that function. Now, this might have actually been the definition of that you were given. Somebody might have said, here's the exponential function, and if you want to get the power down, the e to the x term, you apply this logarithm to it. And I'm guessing that a lot of us didn't question this. And we don't really have any reason to. This is sort of given as the definition. But what we're going to do in this lecture is approach this from a completely different angle and see how we can build from the ground up to arrive at most of the understanding we already have for the logarithm. And along the way, we're going to get some properties, such as what is the derivative of said logarithm, and how this can be associated to these exponential functions. So let's go ahead, let's jump right in, let's talk about the logarithm. So let's start with a definition right off the bat, and that will be our working definition of what the natural logarithm is. So let's say definition, let me put this in red, the natural logarithm. This thing is going to be defined as the function. Remember, we use ln of x if we've seen this before. If not, this is the notation we use for this function. Okay, so this thing is going to be the definite integral from 1 to x of the function 1 over x. Or 1 over t. In this case, we're using x as one of the bounds. So the function, we use a dummy variable, in this case, t, to describe it. Okay, so let's notice something right off the bat. There's nothing to do with exponentials here, right? This thing is defined completely independently of the exponentials. So what is this thing actually? What does this look like? Well, if we offer up a little sketch and we think about how we introduce these types of variable dependent integrals, this thing is actually asking for an area underneath a curve. So the function is defined as an area under a curve. And what curve is that exactly? Well, that curve is y is equal to the 1 over x. And we can see that we are starting at 1. And so if x is bigger than 1, this thing, let's just say we're going to go over to this value right here. This could be x bigger than 1. This is going to give us the area under the curve of this function. So this area, let's say, area equals ln of x. Similarly, if x is less than 1, so let's say over here, x less than 1, Well, we're computing an area, but what you can see is that the upper bound is smaller than the lower bound on this integral, right? So in this case, we have ln of x is equal to the integral from 1 to something smaller than 1 dt, which is the same as, if we remember our properties of definite integrals, the integral from x up to something smaller than 1 up to 1 of 1 over t dt. And this is in the case when x is less than 1. So we're just illustrating. And so essentially what this is saying is that ln of x in this case is minus the area in this yellow region, right? So it's slightly complicated. You're sort of pivoting around x equal to 1 here. Now, of course, from our properties of definite integrals, we can see that when you put 1 into this thing, you get an integral that starts and ends at 1. And I believe this was the very first property that we introduced for these definite integrals. This tells us that ln of 1 is equal to 0. So we have a precise value for x equal to 1 here, even though some of the other ones might be relatively unattainable just because this thing is defined as an area and you have to sort of find what this area is. Okay, so what we can see from my little picture here is that if x is larger than 1, we have a positive area here. So the question is, you can ask sort of questions. You can ask, when is this area equal to 5? Or when is this area equal to 3? Or when is it equal to pi, for example? But as mathematicians, we really only care about typically 2 numbers, 0. So we found a root of the ln function. That's when x is equal to 1. So we can ask ourselves, when is ln equal to 1? And we're going to see why this is important as we move on. But in fact, we have a definition to accompany this. And we will say the number e, so this e stands for Euler's number. Euler is the mathematician who this is named after. So the number e is the number in x greater than 0, such that ln of e, which is equal to the integral from 1 to e of 1 over t dt, is equal to 1. Right? So think about what I've done here. I technically haven't actually told you what e is, right? I said I'm going to use it as a placeholder for a moment. I'm going to say, there has to be something that gives me an area of 1 underneath this curve, which can be proven, but for now you can take it on faith. And I'm saying, okay, just call it e. Use a dummy variable here, right? And we know we've probably been exposed to Euler's number before. In this case, you can compute this thing. It's about 2.718281828. It's an irrational number, much like pi. It just keeps going and going and going. It has no repetition and no pattern. Now, another place where you've probably seen e before is when you compute compound interest. When you have compound interest limiting to continuous compound interest. So you take the times when it compounds and you let that go to 0, sort of like a Riemann sum almost. You can see that this exponential term pops out of this as well. And it turns out these are the same thing. They have a deep relation that we're not going to explore too much in this class. Or at least, in this lecture, sorry. Okay, so then the question is, now I've got a function. This is a calculus class. We want to ask ourselves, what are derivatives and integrals of this thing? So let's start with the derivative. Well, we can see from the fundamental theorem of calculus, so from the fundamental theorem of calculus, we have that the derivative of ln x is equal to the derivative of this integral function which we remember, we might have to go back and review our notes from the fundamental theorem of calculus, but this thing is equal to 1 over x. So you're plugging that upper bound into the actual function. And so by the chain rule, if u is a function of x, we get that if you want to differentiate this thing, if you want to take the derivative of a composition involving the logarithm, the natural logarithm, this is equal to 1 over u times the derivative of u with respect to x, right? So this is just the chain rule, but this is assuming that u is positive, of course, right? Because the range of u has to belong to the domain of the logarithm. That's how these compositions have to work. Now, there is a special case of this that we're going to see coming up over and over and over again when we are using these logarithms, particularly as they're coming through in integrals. So in particular, the derivative of the logarithm of the absolute value of x, so the absolute value of x, as long as x is not equal to 0, has a range of all the positive numbers. So this is valid as long as x is not equal to 0. This thing is equal to 1 over x when x doesn't equal 0. And so why was it that I felt it was necessary to look at this? Well, think about this. We've seen this over and over. We keep having to take integrals like this, assuming that n does not equal to -1, right? Well, now we've finally gotten over the hump, because if n is equal to -1, this tells me that the integral, or the antiderivative, of x to the -1 is equal to the ln of the absolute value of x plus c. So we've already got something useful out of this, right? Because now this allows us to handle antiderivatives of x to the power of n for any possible function, for any possible value of n. We used to have to rule out n is equal to -1, and now we can see why, because it's a completely different function. It's the natural logarithm that pops out. So then the other piece of this that's important is if b is a positive constant, actually, you can do this for a negative constant as well, but we get the logarithm of bx is equal to, if I want to take a derivative of this thing, well, the inner function is b times x, so I get 1 over the inner function, multiplied by the derivative of the inner function, bx, which just leaves me with b. So 1 over bx times b, which is just equal to 1 over x. So this is kind of weird, right? Because this tells me that if I take any positive number, this is assuming x is bigger than 0 again. If I take any positive number, I multiply by x, I put it inside of a logarithm, that function has exactly the same derivative as just taking b equal to 1. That's kind of weird, right? And this seems a little problematic. So we're going to see actually where this property comes from in a moment, but it's worth asking ourselves, what does the graph of the logarithm function even look like? What is it that we're even talking about here? And in this case, actually, we have to extend this quite a bit down. So we've got that it goes through 0. We know that already. And we're going to get something that looks like this. Y is equal to ln x. So if you were to throw this into, say, Desmos or another graphing type calculator, this is what the function would look like that comes out. And so the question, first of all, is, as x goes to infinity, does this function itself go to infinity, right? Of course, this is an important problem that we would like to know. So let's ask ourselves, what happens as x goes to infinity? Okay, well, remember the logarithm is defined by the area underneath the curve of 1 over x from, say, 1 to some number, right? And that number gives you what you're integrating up to. That's what you're putting into the logarithm. So let's say we can estimate the value. So we can estimate ln of 2 by considering let's say by considering the area under the graph of 1 over x and above the interval 1 to 2, right? So if I sketch this out, I've already shown you 1 is right here. Let's use blue maybe. This is going up to, say, 2 right here. And we want to know, what is this value? This is ln of 2 is equal to this. And this will all be important for what happens as x goes to infinity as well. Well, the function 1 over x, this area, so this area is bigger than 1/2. Okay, so why? Why is this the case? Why do I know that this area, so ln of 2, is bigger than 1/2? Well, 1 over x is decreasing. Right? We agree with that. If we think of the function, it has this nice downward slope to it. So the height of the rectangle. So if we make if we put a rectangle underneath this, put a rectangle underneath of height 1/2 and base 1, it lies under the curve. Let me sketch out exactly what I mean here. Here's my axes. So I get, here's my curve, y is equal to 1 over x. And here is, say, 1, here is, say, 2. If I put x equal to 2 in, I go all the way up to 1/2 right here. And here's my rectangle that I just put in. And you can see that there's room missing, right? Because I need to include all of this green space as well in here. So what does that tell me? This tells me that ln of 2 has to be bigger than 1/2. Okay, then how is this going to help me determine the asymptotics? So what happens as x goes to infinity, the big X region? How does this help me? Well, let's remember there's some properties of logarithms that you may have or may not have seen before. So let me sketch those out first, because I will show you exactly why this is important. The first property is ln of b times x is equal to ln of b plus ln of x. Okay, this is one that should be apparent, and it should be apparent from this result at the top of the page here, because we saw that the derivative of ln of b times x is the same as the derivative of ln of x. Now, we know that derivatives are unique up to adding a constant. So this line at the very top of the page right now is actually a proof of the fact that number one right here, because it tells us we know that the derivatives are equal to each other everywhere, and therefore these functions can only differ by a constant. Okay, what else do we know? We know that ln of b over x is equal to ln of b minus ln of x. Again, this follows exactly from my derivative calculation up here. You can do it in exactly the same way. You just calculate the derivative of the left side of that equality and the right side of that equality. You know that they differ by a constant, and you can just plug, say, x equal to 1 in there to find what that constant should be. 3. This tells me that when b is equal to 1, this gives me minus ln of x. So I've got a symmetry property, right? When I flip I do 1 over x, so that takes big values of x and makes them small, and small values of x and makes them big. I'm just negating the function. So if you look at my sketch right here, you can see, it's not the best sketch in the whole world, but that's kind of what's happening. So when I take ln of 2, then if I ask for myself, what is ln of 1/2? So let's say right here, then this is ln of 1/2, which is equal to minus ln of 2. So we really only need to calculate values for the logarithm for values x values bigger than 1, because then we can just negate them to find the values that are smaller than 1. And the most general version of this property that we're going to use to figure out the asymptotics here is that the logarithm of x to some power, say r, well, you can bring down that power and multiply it by ln of x. Okay, so how does this help, right? How do we know what happens as x goes to infinity now? Well, we're going to use property 4, and we're going to say by property 4, we have, so if we take increasing values of x, so let's take powers of 2. So 2, 4, 8, 16, 32, 64, 128, right? We just keep taking, we just double and we get bigger and bigger and bigger values. Well, this thing is equal to n times ln of 2, right? So I use property 4 right there to compute that. So maybe if we want to, we can put a little marker. Property 4. And we know that ln of 2 is bigger than 1/2. So this has to be bigger than n times 1/2, which is equal to n over 2. So taking n to infinity shows that ln of 2 to the n goes to infinity. Why? Because it's bigger than something that's going to infinity. It's pushing us up. So that's interesting, right? This essentially tells me that the limit as x goes to infinity of ln of x is equal to infinity. And from property 3, the limit as x goes to the limit as x goes to 0, so 1 over infinity, you can think of it that way. This is equal to minus infinity. And that is just by using this 1 over rule right here. So you can see that there's an asymptote at 0. Now, if you pause for a moment and think about these properties, these are really, really great properties, right? Look at what property number 1 says. Property number 1 says that the logarithm takes multiplications and turns them into additions. It also says, property 2, it says the logarithm function takes division and turns it into subtraction. Now, I don't know about you, but personally, I think addition and subtraction are much easier than multiplication and division. And similarly, number 4 tells you that exponentiation, so 2 to the power of 6, if I wrap that in a logarithm, this turns into a multiplication problem. So long before calculators were a thing, people used logarithms to simplify very, very complicated multiplication problems or division problems or exponentiation problems. You used to have a huge book telling you the logarithm value of certain numbers. So imagine you had two 6-digit numbers that you needed to multiply together. You could first take the logarithm of that multiplication. So say log of a times b, or ln of a times b. This becomes ln of a plus ln of b. So you would go through your book, you would find what the natural logarithm of a is and the natural logarithm of b, and you could add them together, and that would tell you what the logarithm of a times b is. And then what you can do is we can, as we're going to see as we move forward here, you can undo that process using an inverse function. And again, this is something that would be in your table, in your book. So this is how you can multiply really big numbers together in a relatively sane manner. You can turn that into an addition problem. Before we do that, let's take a look at some nice little examples and see how we can use these differential and integral properties of these logarithms in order to solve a problem that we might get in the wild. So let's see. Example, let's integrate from minus pi over 2 to pi over 2 of 4 cos theta divided by 3 plus 2 sine theta d theta, right? So it's kind of an ugly integrand. It is certainly not of the form like x to the power of n, so it's kind of out of our wheelhouse at the moment. So let's start by introducing a little substitution here. So let's say, actually I'll do this in blue, let u equal to 3 plus 2 sine theta. So we might have to brush up on the substitution rule for this, but this tells me that du is equal to 2 cos theta. And that's a very good thing because I see that all of the terms in my integrand have disappeared except for constants into functions of u. Similarly, we remember the substitution rule for definite integrals. We have a whole video lecture on this. We need to change the bounds of integration as well. So we ask what u at minus pi over 2 is. We can calculate this maybe by recalling some values of trigonometric functions. And similarly, evaluating at the upper bound, this thing gives us 5. And so now my function becomes the integral of 1 to 5 of 2 over u du. Now, where did that all come from? Well, first start with the over u. That was the 3 plus 2 sine theta. That's the u function. Then the cos theta d theta, and I take a 2 from that. That leaves me with du. And since I had 4 out front and I only took 2 from it, I've still got a 2 floating through. So I'll make my life a little simpler. And I get 1 over u du here. And now we've seen this, right? This is the logarithmic integral. And so now I get 2 logarithm of the absolute value of u, all running from 1 to 5. And so here I get 2 ln of 5 minus 2 ln of 1, for which I know that ln of 1 is equal to 0. So I can say goodbye to that piece. And this leaves me with 2 ln of 5. Or if I'd like to get fancy, and I can use one of my logarithm rules, I can bring the 2 up as an exponent in here, and this becomes the natural logarithm of 5 squared, which is just equal to the natural logarithm of 25. It's either or, you can keep it in any form you want, but I just wanted to emphasize how you could actually use some of those logarithm rules to simplify this just a little bit. Okay, earlier I got a little bit ahead of myself and I got excited when I was talking about the the big book of logarithms, right? And I said, if you want to multiply two huge numbers together, you can hit them with a logarithm. And all I was able to get to so far was to tell you sort of what happens. You can just add the logarithm of these two numbers back. But of course, the question wasn't, what is the logarithm of these two functions or these two values multiplied together? The question was, what is these two values multiplied together? So we need to talk about an inverse function for the natural logarithm as well. And again, this is probably something that you've seen before. If you've seen the logarithm before, you've certainly seen it coming as the inverse function of the exponential. We are going to go the opposite way. We are going to say, what is the inverse function of the logarithm? And this is how we're going to get up to the number e. So first, let ln minus 1 of x denote the inverse of ln of x for each x greater than 0. Okay, then we know that the domain, so domain of ln of x, so dom stands for domain. This is equal to all of the positive numbers, 0 to infinity. And the range of this thing is equal to minus infinity all the way up to infinity, right? We just showed these asymptotics that as x goes to infinity, ln of x goes to infinity. As x goes to 0, ln of x goes to minus infinity. So this is the same as saying the domain of the inverse is equal to all of the real numbers. So basically, I'm going to do a cross pattern here, right? And the range of the inverse is all of the positive numbers, 0 to infinity. And moreover, the limit as x goes to minus infinity of this inverse, this is just undoing the asymptotic properties that I just talked about for the logarithm function. This is equal to 0. And the limit as x goes to infinity of the inverse is equal to infinity. So this is just sort of helping us feel our way through the dark and asking us, what's happening so far? How can we sort of piecemeal this idea of an inverse back together? Also, we know that ln of e is equal to 1. We knew that, right? So e is equal to ln inverse of 1. Right? This is an important property. This helps us. We have a correspondence. We know that the point e comma 1 lies on the curve ln of x. So that tells us that if we swap around those two numbers, 1 and e, that tells us that 1e is on the curve of the inverse of this function. Right? This is, again, just a definition of the inverse. The inverse is telling you, if I know the output, what was the input? Instead of a usual function says, if I know the input, what's the output? So also, this can be extended, right? Because now we know that if we raise e to any power, say r, this is the same as r times the ln of e, which is r times 1, which is just r. So this tells me that e to the r comma r lies on the curve y is equal to ln of x. And this is for every r greater than 0. Actually, that's for every single r. It doesn't even have to be positive. I'm sorry. I got a little conservative there. It's actually for every value of r. Okay, So then the inverse swaps those two values around. Hence, ln inverse of r is equal to e to the r for every real number, r. But what does that say, right? I'm using the notation r just for like a real number. But if I switch that around for x, that tells me that the inverse of the logarithm is exactly e to the x. So let's put this as a nice definition so we can remember it. The inverse of the natural logarithm is the natural, actually, let's put it in red just so we can emphasize what it is we're defining here. It's the natural exponential e to the x. So, i.e., ln inverse of x is equal to e to the x for all x in R. And so this sort of gives us, maybe this is not a surprise to us, but hopefully the surprise here is how we got to it, right? It's kind of a weird way to think about it. Remember, in your previous calculus class, if you had one, you probably learned the exponential first, and then you were sort of given this shrouded in mystery, this logarithmic function. Whereas here, we started from the logarithmic function, and we showed you how to get back to the exponential. And so the inverse relations, we have the following. These are just definitions of inverse functions. We know that e to the power of ln of x is equal to x. And this is for all positive x, right? It has to be in the domain of the logarithm. And if you take the logarithm of e to the x, this is equal to x. And this has to be in the domain of e to the x, which is just all real numbers. So now we can ask ourselves, what is the derivative of e to the x? Well, we've probably already seen this before, and we probably know that e to the x differentiates into itself, but let's actually prove it because it's kind of a cool little elegant proof using the natural logarithm. So we know that this thing is equal to the inverse of the natural logarithm of x. And now we can use what's called the inverse function theorem. So let me just write this abstractly for a moment. It says that if we would like to take the derivative of an inverse of a function, this is actually equal to 1 over the derivative of the original function, and then composed with the inverse at some value of x. So this is called the inverse function theorem. Maybe we can put a note here. Inverse function theorem. And now we can start filling in the gaps. So f inverse, again, this is just e to the x. And the original function was the logarithm. So we know the derivative is 1 over x. So we get 1 over e to the x. This is a composition, 1 over x composed with e to the x, which gives us e to the x. Hence, we get exactly what we probably already knew, especially because I've used it in this class before. But now we have a proof. Now we know for sure that this is correct. And we can actually use this to go backwards. We can find the antiderivative. And so this tells us that the antiderivative of e to the x dx is equal to e to the x plus c. Remember, these antiderivative computations, we always have the plus c on the end because it represents all possible antiderivatives. And much like the logarithm, there's a number of properties that exponential functions come with, right? In particular, this function e to the x. And it basically is undoing, or it's the sort of inverse relationship with the properties from the logarithm. So let's take a look at them. So we have these properties. The first one says that if we take two exponentials and we multiply them together, this is the same as adding their exponents and then taking the exponential. Now, if you would like, you can go back and look at the logarithmic properties, and you can apply the logarithm in order to prove these things. Okay, so you use the fact that the logarithm and the exponential are inverses of each other. That will show you that these things lie in one-to-one correspondence with the rules of the logarithm. So similarly, that tells us that e to the minus x is equal to 1 over e to the x. And if I take two exponentials and I divide them, sorry, that should be x2, not x3. Then I get e to the x1 minus x2 here. And finally, the fourth one, e to the x1, and then I multiply it, or I raise it to another power. This is the same as multiplying the two exponents. And you could have done this in the opposite direction and raised to the power of x1 instead of x2. Okay, so the question is, how do we define a function? What if we don't want e to be the base, right? So remember, e is this function like 2.718, all of this mumbo jumbo on the end. What if I just want to define a function that's like 6 to the power of x, or 6.3, or 6 plus pi, or whatever, right? How do I do that? Well, let me give you the following definition, okay? So we get a definition. Let's say for any number, a greater than 0 and x in R, the exponential function. So again, I'm going to put this in red to emphasize it. So the exponential function, which is with base a, so instead of base e, for example, is given by, and this will be a to the power of x. That's how we're going to denote it. And technically, this should be e to the x times ln a. And so where does this idea come from, right? So let me go to another page. Let me show you why exactly we can write it this way. So let's ask ourselves the question, why should I define an exponential function in that way? Well, because e and ln are inverses of each other, I know that for any positive number, e to the power of ln a is equal to a again. So if I raise both sides to the power of x using those properties that I just showed you, I get this is equal to this, which from property 4 is the same as this. So now you can see that the proper way, the technical, the mathematical way to raise a number to a power is technically going to be used in e to the x here, or e to the x and ln of x. So now the question is, what is the derivative? So let's say derivative. So we're just sort of getting peppered with definitions today. Hopefully most of this is review. I hope that the real exciting part of this, or maybe the most captivating part of it, is sort of deriving all of these things, seeing where they actually came from. Because as I mentioned before, maybe you were shown these properties, but nobody really explained where exactly they came from. So let's do this. Let's take a derivative of this function. Well, by definition, this is the derivative of e to the x times ln a, which is, in this case, a chain rule. The outer function is e to the x. The inner function is x times ln a. So we take the derivative of the outer function, e to the x ln a and evaluate it at the inner function, and then multiply it by the derivative of the inner function. And we can, again, back substitute e to the x ln a, that's a to the x. So we can see that we get ln of a here times a to the x. And this makes sense, right? Because if a is equal to e, the Euler number, then ln of e is equal to 1, and we get that the derivative of e to the x is equal to e to the x. So exactly what we would expect. So this is consistent. This essentially says if you have a different base a, then you just get a constant factor of ln a that floats through. That's the only exciting piece of this so far. And so this means that we can also do integrals. And we can see that really the only thing that matters here is the constant term ln a. So this tells us, sorry, I'll just use x here for simplicity. If I would like to integrate this thing, this is the same as just dividing by that constant factor. And then, of course, plus c, because we're talking about all possibilities of these logarithm functions. Or sorry, these antiderivatives of exponentials. And of course, the last piece of this is the inverses. Well, we denote log base a of x is the inverse of a to the x, which is the same as saying that if I consider the function log base a, of a to the x, this is equal to x, and a to the log base a of x is equal to x. So this is just a notational thing. When a is equal to e, then we get back ln, right? So ln, the natural logarithm, is paired with the natural exponential e to the x. For any other exponential with base a, we write log base a. Okay, so there's a notational piece to this, but all of this comes back to the fact that log and a to the power of x are or can be just derived using the simple formulas for exponentials and natural logarithms. And so why is that? Well, let's notice if I say y is equal to log base a of x, this is the same as saying a to the power of y is equal to x, which I can hit both sides of this with a logarithm, a natural logarithm, sorry. Now we know the exponent comes down. This leaves me with ln of x. So I'm just using properties of the logarithm so far. I believe this is property 4. And this tells me that y is equal to ln x divided by ln a. So i.e., this inverse function that I just told you, that I just sort of gave a name to it, I didn't really say it existed or anything. Well, here it is. It's just determined in terms of the natural logarithm. And so sometimes we call this the change of base formula. And the reason I call it a change of base is because in this case, the base is a for any value of a that's positive. It could be pi, it could be 100 trillion. And essentially what this is saying is this function is just a scalar multiple, 1 over the natural logarithm of your base multiplied by the natural logarithm function. So what have we seen? Okay, let's just go back and recap for just a second here. For any base, you can describe an exponential function, and it's really just a composition with the original natural exponential, e to the x. And then what does this tell you? The inverse of the exponential function, a to the x, we denoted this by log base a of x. But now what I'm showing you is that it's essentially, actually not essentially, it is exactly just a scalar multiple of a natural logarithm. So you can do this for any value of a, but essentially you just keep coming in circles and you keep coming back to the original place you started. And so of course, because the natural logarithm of x satisfies all those nice properties, then so does these logarithm base a's, right? So the properties. So we're just sort of getting peppered with properties today about all of these different functions. But one of them is we have the product rule. So if we do log base a of x times y, this is log base a of x plus log base a of y. This is the first rule from logarithms, essentially. We have the quotient rule, x divided by y. This is log base a of x minus log base a of y. Again, just the second rule that we just saw for natural logarithms. Now we have log base a of 1 over x. So we have this reciprocal rule. Again, this is equal to minus log base a of x. And actually, this reciprocal rule is more generally given as the power rule, which says that x to the power of y is equal to y times log base a of x, right? So hopefully there's nothing surprising here, right? Because these are just the same properties that we gave for the natural logarithm. And if you find yourself kind of bored, try and prove it, right? All you need to do is go back to this slide and use this definition of the log base a, use all of the properties for the natural logarithm that I gave you, and then just turn things back into log base a. So it should be, a 2-line proof for each one of those properties. And so finally, let's ask ourselves, what's the derivative here? So we've taken a very circuitous route, right? We started with the natural logarithm, did all the properties, derivatives, antiderivatives, that kind of stuff. Then we defined the exponential function, derivatives, antiderivatives, whatnot. Then we used the exponential function to describe regular exponential functions, a to the x. We did all of its properties. Then we said, what is the natural logarithm? Or sorry, what is the inverse for those things? And now we're going to do all of its properties. So we sort of started and ended with logarithm type functions. And in the middle, we turned into these exponential functions. So we can see this deep relationship between these two things where we have these inverse properties that go back and forth. So now the question is, what is the derivative of log base a of x? Well, we can use the definition here. This is the derivative of ln x divided by ln a. A is a constant, right? So don't get too confused with this. So this tells me the only thing I'm really differentiating is the ln x term. Ln x, sorry, shouldn't be a multiplication there. And now we know the derivative of ln x is 1 over x. So we get 1 over ln a times 1 over x, which I'm just going to write a little prettier, x times ln a. So again, the only new thing here is this factor of ln a that's floating through. But it's essentially the same derivative. Natural logarithm, the derivative is 1 over x. Log base a, the derivative is 1 over x times the natural logarithm of a. So you get this factor of logarithm of a floating through. Oh, sorry. Okay, then let's wrap it up with just a couple little examples. Two examples, one with a derivative, one with an integral. Let me show you how to actually put this into practice. So here's the first one. we want to find the derivative of log base 10, so a is equal to 10, of 3x plus 1. Okay, so first of all, let's turn this into a natural logarithm problem, okay? You don't have to do this every single time, but I want to emphasize it as we go through. So this becomes the natural logarithm of 3x plus 1 divided by the natural logarithm of 10. And now the natural logarithm of 10 can come out. We don't need it for this derivative. And we have the natural logarithm of 3x plus 1. So again, the natural logarithm of 10, it's just a constant. It's along for the ride. And now we have the derivative of natural logarithm, ln, of 3x plus 1. This is a chain rule application. The outer function is the natural logarithm. The inner function is 3x plus 1. So you take the outer derivative, 1 over x, and compose it with the inner function, 1 over 3x plus 1, multiplied by the derivative of the inner function, which is 3. And so now let's put it all together. 3 divided by 3x plus 1 times ln of 10. It's not pretty, but that's as good as it's going to get. That's what the derivative is. Okay, now let me give you another one. This time, let's do an integral with this. And these are just, the first examples that we're going to do. We're going to see a lot more of these as we go through and progress with this course. But of course, these are just sort of little warm-ups for us. So imagine I ask you to find the antiderivative of log base 2 of x over x. All right, I say, what is the antiderivative of that thing? So the way I want to start this is the same way I started with the last one. And I want to replace log base 2 of x with a natural logarithm. So here I get 1 over ln 2. This is coming from the change of base formula. Ln x over x dx. So all I did is I took the 1 over ln 2 that comes from the change of base. I kicked it outside. It's a constant. It's not going to do anything with my integral. Okay, now I can do some substitution. Let's say let u equal to ln of x. Then du is equal to 1 over x dx. And that's good, right? Because here is du. Here is u. And so this gives me 1 over ln of 2, and then the integral of u du, which is equal to 1 over ln of 2. And we're back into familiar territory. Here I've got u squared over 2 plus c. And again, we remind ourselves, like we always do with substitution, nobody asked me about u, right? They only asked me about x. So let's resubstitute back in. And this is going to give me ln of x squared, that's u squared, and I'm going to condense all the constants into one denominator at the bottom, 2 ln 2, and let's not forget the plus c. Okay, so that was a lot, right? I know, I recognize that was a lot of different definitions, a lot of different properties, a lot of different derivatives. But my hope with this is that much of this you've probably seen before. And so maybe the exciting thing was to sort of see where some of this came from. Now, if this was new to you, that's okay, right? Take it slow. These are things that we're going to be working on as we progress through this course, and you'll get better and better with it because you'll just be fed up from using it so much, right? You'll just see it all the time. So now what we have at our disposal are new functions, functions that are not polynomials, they're not trigonometric functions, and these functions can be used now when we are doing definite integrals or when we have differential problems. So that's what we're going to focus on in the videos that follow this. This lecture was just preparing us for that and showing us, how we can get these new functions and what their practical use is.